All right. Hey, everyone, and thanks for coming. Yeah, I'm one of the original creators of PyTorch, but as you can guess from the long list, we've already had a bit of contributors, and it's mostly become a community project at this point. So how many of you actually do know PyTorch, like know how it can be used, how the API looks like, what are the general features? Okay. Okay, so yeah, I guess we'll need to introduce it. So generally, like most people, and like if you look on the internet, it will generally be like presented as a deep learning framework. But ultimately, if you're really like, I only have half an hour, and I really want to talk about some of the new stuff, so I will need to be really quick with the introduction. And yeah, I think it will be much simpler to actually understand it if we don't look at it as a deep learning framework, but more as something like NumPy. So probably most of you actually know NumPy. So NumPy is like a library in Python that implements arrays. They can be arrays of arbitrary Python objects, but most importantly, if you put numeric types in them, they will actually like be unwrapped from Python objects, and they will be stored in memory efficiently, and also like in native, like whatever is the native computer format you're using. And so many of the operations on those arrays become much more efficient, like matrix multiplication or generally like addition of many numbers in parallel, right? So yeah, just in case you don't know NumPy too well, generally like you can construct those arrays like this. They can be multidimensional. So at the top you have a multidimensional layer. You can wrap scalars as well. Then you can do operations on those arrays. You can like take columns, slices, whatever, check their shape. The add operator is like matrix multiplication. You can generate random matrices, all this. And ultimately at the lowest level, Torch is exactly like this. So you basically get this ND-array library, which again lets you manipulate this. Torch doesn't really let you put arbitrary Python objects in this, but that's not really the common use case. Like you mostly care only about the numeric types that you want to do some math on. Yeah, so ultimately at the lowest level, it's just like NumPy. But of course, doing NumPy exactly would be really silly. And like that would be pointless. It's a project that's relatively mature, and like there's been a lot of work put into this, and it has pretty good implementations for all of those operations already. So that will basically be a waste. So of course Torch comes with some new features, and I'll just like give you a quick overview of what are the most important points I think that are beneficial both for deep learning, but not only really. Like there's something that can be used in a lot of domains that just require some kind of scientific computing software. So first and foremost, PyTorch really wants to integrate with NumPy. Ultimately, Python is great just because it has this like really huge ecosystem of like arbitrary packages that can do pretty much anything you want. But really, like the thing that every single package, scientific computing package at least, uses to exchange data are NumPy arrays. And so you really need to be able to integrate with NumPy. So just to quickly go through this, we have methods to convert both from Torch to NumPy arrays and vice versa. So the like most important thing about this to note is that actually it's really cheap. Like it's basically cost is constant no matter how many elements you have in the array. It's like on the order of microseconds, so it's really fast. And the way we achieve this is essentially Torch uses almost the same, like pretty much the same layout and memory as NumPy, so the data is actually shared between those arrays. So if you convert to one of those libraries and modify the array within one of those libraries, if you print out the one on the other side, you'll see that it changes as well. So this is something that kind of lets you ultimately use Torch in like small parts of your program. In only places where you actually care about those features, and the rest can just use whatever Python library you really like, and you can just exchange data with no copying. So that's really efficient. So that's one of the important points. But then there are two, I think, crucial things that are ultimately extremely needed in like today's scientific computing workloads. So first is accelerator support, and that's pretty basic, and NumPy doesn't have it. It actually takes a lot of work to get it to get this right. And when I mean accelerators, ultimately most of you already have them. They're GPUs or some more specialized hardware, but like almost everyone has a GPU that's capable of executing some kind of specialized languages like CUDA GPUs or OpenCL on AMD GPUs or ROCm. So yeah, basically all of this like kind of array-oriented programming paradigm where like you have all of those arrays it basically exposes a lot of parallelism in your operation. So like if you have two arrays and you add them, you just add two elements independently. You have like a lot of elements to add independently of each other. And basically GPUs are like extremely parallel machines, and they really excel at those kinds of things. They've been basically designed to do those things because that's like how most workloads in graphics look like. And so when you have programs like this, they map extremely well to them. And in fact, like just by moving the computation that you have from CPU to GPU, you can easily get like 10x or 20x speed up, provided your arrays are like large enough. And just to kind of give you an idea that it's really easy to do that in PyTorch, this is a program that actually runs on the CPU. So you generate two arrays, you add them, you print them. If you want to run this on the GPU, you just do something like this. So basically all tensor constructors take this device argument, which lets you specify where to put the data. Or if you get like a result of some CPU computation, maybe from NumPy perhaps, you can use the to method to actually move it to a different device. And the line at the top basically makes it possible for you to kind of have scripts that are agnostic to the system you're running it on. So like you can do quick development on your laptop that doesn't have like a powerful GPU, you don't really want to use it, or it's not even capable of running, like it has only an integrated card. And then you kind of push it to some kind of more beefy server, and it will run on the GPU automatically. So it like detects if it can actually use this. And so this kind of shows you that it's relatively easy to have code that's like independent on the actual device you'll be using. So you can just write your thing once, and then like depending on the capabilities of your system that you're running your script on, it will either be faster or slower. But yeah, you can still do that. And another, I think, really differentiating feature, I mean, it's popular in machine learning libraries ultimately, but like something that's missing in a lot of other libraries is high-performance automatic differentiation. So this is also something that's been really important for machine learning because, like, basically what it lets you do, it kind of lets you write your function, and as long as it's differentiable, you can basically ask the system for what's the derivative of, you know, something I computed with respect to something that I used to compute it. And it will do, like, all the differentiation for you, so you don't kind of need to, you know, do this by hand and, like, compose the formulas and all this. And so that's a technique that's like really important in many domains, as I mentioned in machine learning, but also like in engineering or in finance generally. If you want to simulate something, or if you have a function that you want to optimize, which is exactly the machine learning case, for example, this is very useful because like you can, you know, take gradient kind of gives you some kind of local idea of the shape of the function you're optimizing, so you can kind of try to traverse the landscape to actually reach the lower points. And also, this is again really easy. So basically, you just write, as I mentioned, you just write out this function. Here, it's this polynomial function. Then you just evaluate it on some data, and like in here, we just evaluate it on this x. And then we can ask, what's the gradient of, you know, the output of this polynomial with respect to its input? And so, like, if you print this, you'll see that it exactly follows like the simple rules of differentiation you probably know. So yeah, that's kind of the, you know, the, like, if you don't know this, that's kind of the most important part. Torch also has a bunch of helpers for training machine learning models, but I don't really have time in here to cover them, unfortunately. So I want to kind of move on to like what's new in PyTorch 1.0. So PyTorch's been released in January last year. So it's already been some time, and we've had a really rapidly growing community, which we're like super happy about. And, you know, ultimately, when we have so many people depending on this package, so far we've been in beta, we wanted to kind of push new features quickly, we wanted to experiment. Unfortunately, sometimes, you know, between versions, you needed to adapt your code to actually have them work. But I think we've converged to like a relatively nice API at this point. And so we kind of want to stabilize. So we think that it's a good idea to actually like release the 1.0 version. So you know, to kind of send a signal to people that actually this is pretty much ready to be used in any kind of environment. And the important part is that this is already available, and what's already available is the release candidate. So it's not the final version, it's actually updated, I think, daily based on the builds from like the master branch. And the stable version will be released sometime in December, I think. This is not to say that the current version is unstable. Basically, like some features might not exactly be there or might not be like as polished as we would like them to be. in the final release. So we're still working on this, but like ultimately, if you use it and you have some code that works with the release candidate build, you kind of got it to work. Even though like some error messages might not have been super helpful, this will also work in stable. So you can still kind of play with whatever's in there. Today we already have documentation for the new things. But it will ultimately get better, and yeah, it will ultimately get somewhat better in the final release, like in a month. Yeah, and the really important part that we've been emphasizing in 1.0 was kind of the path from research to deployment. But I think it's really important to kind of clarify what deployment is. So ultimately, PyTorch. The API that kind of I showed you is like really close to NumPy, and that's ultimately something that many people are familiar with, and it makes like rapid iterations to like improve on the model you're working on or on some kind of program you're working on to solve some problems really convenient, because you just kind of shift around multiple lines of Python and everything adapts magically. You just rerun your script. And so, we believe that ultimately you will be going through many iterations of such research cycle, but then you converge to something that you really care about, and this is something you want to use in some kind of a final product. And just to clarify what deployment is in here, so it's completely fine to run Python in production. People are running PyTorch in production as well, just from a Python process. But that's not something you really want to always do, and there are multiple reasons for this. One, if you have a really large-scale infrastructure, just any kind of saving will be beneficial for you in terms of power, money, anything. And the second thing is, many people want to take the models they built or just some kind of pipelines they built and actually port them to run mobile phones. And unfortunately, Python is not the greatest thing to run on mobile phones because the interpreter is actually relatively slow in them. It's relatively big. If you want to bundle this, it like adds a lot of weight to your application. So you don't really want to do that. You really want to embed kind of a minimal runtime that can execute something into the app you're shipping. So the API I showed you, the NumPy-like API, which will still remain the primary API for PyTorch. I'll be calling it eager mode from now on. And the good things, as I mentioned, is that it's really simple to write and debug. It's ultimately the model that everyone is very familiar with if you know how to program in Python. The problem is that it's really hard to deploy in the sense that I meant, because like whatever you wrote is really tightly bound to the Python code that we wrote. And so a way that we thought of to actually kind of get around this, to kind of get your code and your pipeline as data that you can actually export and run without Python, is something called script mode. So script mode ultimately, at the lowest level, you can think of it as a new programming language. But the good thing is that you actually don't need to learn anything because it like follows exactly the syntax and semantics of Python. The only caveat is that it's only a subset of semantics of Python. So there are certain things that are disallowed in those functions. So you can't, do arbitrary reassignments of functions and like hope that everything will work. But ultimately, like if you follow a certain pattern, mostly like avoiding mutation of objects, etc., which we can statically analyze, we'll be able to kind of recover all the structure of your code. And so two good things that come from this. First is, again, you can export this and you can run this from like pure C environments. And second is that it's actually pretty optimizable. So we can take the code of your pipeline and like apply some optimizations that are relatively hard to apply by hand, but we can do this automatically in the backend to actually make some things run faster. Some most common patterns usually. So just to give you an idea of what works today, so those are kind of the things that are supported in script. So you can work with tensors, you can work with integral and floating point numbers. There is basic control flow that works. You can print stuff. You can get strings. You have tuples of arbitrary things. You have polymorphic lists, and you have function calls. And so that's a like very, very restrictive subset, as I mentioned. There will be more coming. Even building like something that supports this much is like a pretty big effort. But ultimately, like when we tried this, it's actually enough to like express most of the machine learning models that we care about. And also, like, sometimes you can actually break out from the subset, which I'll be talking about in the moment. So the important part is this path from your eager program that, you do some research, you write the eager program, and then you actually want to deploy this. And the question is, how do you get from the eager program to the script program? And so there are two ways to actually do that. So one is tracing, and another is just using script straight away. So tracing is exactly this like escape hatch that lets you doesn't make us inspect your code, so you can actually use arbitrary Python features. Like whatever you use is completely fine. There are no restrictions whatsoever. So you don't need to do any code changes. The downsides are first, basically how tracing works is you give us your function and you give us an example input. And so we'll run this function once and we'll see exactly what kind of PyTorch operations you do on the arrays, right? So, and we'll basically like assemble a list of instructions that will, be able to replay this single execution of the function that we recorded. So this comes with some downsides. Like if you have control flow that's kind of data dependent, so if it actually varies at different calls to this function, this won't work correctly because we'll only see like one branch of an if, or if your for loop executed 5 times, we'll only we'll always execute it 5 times, even though your original function, if passed a different input, would execute 10 times. Like we won't do that. And unfortunately, there is no way for us. Since we're not inspecting the source, there's no way for us to actually warn you that we're kind of losing some kind of information. Like if you use trace, you're kind of asserting to yourself that it is actually a valid thing to do. And so as I said, there are a lot of warnings in here, but oftentimes this is really what you want. Because if you take convolutional neural networks as an example, that's a picture from the residual networks paper. What you really want to recover, if you want to export them to mobile, what you really want to recover is kind of this structure of computation that you can see on this graph, right? So every single box that you see in here is ultimately some kind of an operation, and the arrows simply indicate how do you pass around the data. And so it doesn't really matter if you use for loops, if you use conditionals inside to implement this kind of model structure, it will always produce exactly the same sequence of operations, and it's really only the sequence of operations on arrays that you care about. So in this case, it's completely fine to kind of throw away all of the Python bits that you have around it. And again, it's completely fine to use this control flow. So if I were to implement a model like this, kind of a simplified version would look like this. So I would probably have a list of some operations those conf2d things are exactly the most of the blocks in this picture. So I would just have a list of them, and my model would simply loop over them and apply some function in between. And so this is actually perfectly traceable. So again, if you were to change the list of if you were to trace this and change the list of convolutions, the function that you traced wouldn't adapt. It would be fixed, and essentially it would look like this. But of course, in most cases, your programs, if you, for example, train a machine learning model, you really only construct the model at the beginning. You might have, this list might have a different length depending on some command line parameters, but it doesn't really matter because once you finish constructing your model, it will stay constant for the whole duration of the program, which will train the model later. So even if you wrote this function like this, it will be fine to it will be semantically equivalent to the trace version if you use this. And in fact, we have a Torch Vision package, which is a very handy way to train a lot of vision models. It has both data sets and models pre-trained and the ones you can train from scratch. And I'm pretty sure that you can take any model from the Torch Vision package that's written there, and you can safely trace it on a single input that's even randomly generated. And that will give you a trace that's completely valid for training or for later export. So that summarizes tracing. And as I mentioned, there is another way to do this because sometimes you really do care about this control flow and you really wouldn't like to lose it. And that's the scripting way. So torch.script is an annotation that you can put on certain functions to kind of assert that they will be written in the subset of Python that we support. So you're just, again, you're still writing Python, like you're not importing, you don't have another programming language embedded. You don't really need to learn anything new. And we'll simply statically analyze the source of the functions that you annotated like this. So control flow is recovered correctly because we'll see that you have like an if or, a loop inside your function. But again, you're restricted to this subset. And the cases where this is useful, for example, are recurrent neural networks. So basically, this is a function that computes a recurrent neural network. And why this is important is because you have this loop which like depends on the size of the tensor. So if you think about the networks, they're like recurrent neural networks are sometimes used, you can refer to them as sequence to sequence models. So they map an input sequence to an output sequence. And the nice thing is that the sequences can have different lengths. So like if you're processing natural language, a sequence might be a sentence and not all sentences have equal length. So in this case, it's like really important to actually retain the, like to actually be able to run this loop a different number of times. So tracing wouldn't work in this case. But, this function is written in the subset that we support. If we do require you to put some type annotations on this so we know actually what's what, and like if you can actually unpack those things correctly. So we do support both the Python 3 syntax and the Python 2 syntax for like compatibility reasons, although you should really use Python 3 at this point. Yeah, and the important part is that trace and script really mix seamlessly. So if you have like a big thing that you don't really, again, care how you implement it, so you want to trace it, except there's this single loop inside that you really care about preserving. So it's completely fine to like put the script annotation on this small thing and then just trace through the whole thing. Once you get to it, it will actually not trace it will like still run the scripted function, but it will actually not use the instructions it emitted. It will actually just copy paste the graph. So it will retain the for loops, or like control flow that's inside. And again, if you use something that you traced previously in a script function, because again, script functions support function calls, it will again like not go through some external mechanism. It will be a first class function call in this like programming language that we designed. And the important part again is that we support function calls, and they're not only within the language, we also support function calls to Python. So obviously, when you call back to Python from a scripted function, you will no longer be able to like export your model because it will again not be able to run without Python. You have some Python references inside, but it allows you to like really quickly kind of iterate on those things. So when if you were to take your script that's written in Python and like transfer it, we don't want you to kind of jump on a huge journey to kind of transpile all of your code to the format we support. We kind of want you to plop those annotations kind of function by function. You can verify that it works every step along the way, and also later, like if you have something that's completely converted to script, you've exported your model, but then you want to go back to the research cycle, like you want to change some things, try out some new libraries we don't support in the subset, it's again completely fine to just remove a few of those annotations in the places you want to edit. It just runs as regular Python. You can debug it as regular Python code, and it still keeps working. As long as you don't export it, it's completely fine. You can still run this. And as I mentioned, the important part is that you can really run this in native C++ environments. So once you export such a model, there is basically a one-liner at the top in here that can load it in C++ using our own library, and you can run it on any tensor in C++, because we also have a C++ API now, which I'll be talking about in a second as well. Yeah, so exporting is one thing, but I also briefly mentioned that it's also an optimizable subset. So this is very much work in progress, so you shouldn't really expect wonders once you annotate those things. We've been really mostly working on getting it to be robust and kind of give nice error messages and, generally be a nice thing to work with. And performance optimizations can be done like later in the background. Things can magically start getting faster and faster. But basically the problem we're trying to solve here is that like if you use a like vanilla model that like maps really well to some fast primitives, like if you run a recurrent neural network on a GPU, there is like an NVIDIA cuDNN library and that implements this network, and it's really, really fast. And like it's really hard to match it. And so if you write the same network but using like regular Python, PyTorch hops in Python, your performance will drop like a few times at least. Like 5x, 10x is actually relatively reasonable. And so in most cases, if you're just training vanilla models, this is completely fine because they always map perfectly. But if you actually want to change some small things inside, you suddenly fall out of the subset, and so you have to pay this performance penalty. And this is something we want to avoid. So for one variant of an LSTM that we've been benchmarking, kind of just annotating it with script already gives you like a 3 times speed up. So again, it's not like it won't magically improve every single model. It really depends a lot on what your model is and how well our optimizations that we currently have map to it. But there are certain cases where you can really find very noticeable speed ups. And now I'll have to really quickly cover the extensions. An interface that we've recently added is currently in beta. It's not really very much part of the release. This can still change, so you really shouldn't kind of depend on some production projects on this. Like the part for loading the data, for loading the exported things should be stable, but like some of the other things I'll point out which ones are they. They can actually change between this and next release, so you really shouldn't depend on this. So extensions have been around for like a few months now, I think. Basically what they let you do is they let you port some of your code from Python to C++, either because you want to interface with some other C++ libraries, or because you have custom CUDA kernels, because again, you want to speed up your thing. So, it's an example of a function in here that, does some, basically allocates a new tensor, multiplies some other tensor by 2, and then just launches a CUDA kernel. And so everything you need to do to expose this to Python is actually just put those 3 lines at the bottom. This uses a PyBind 11 library that we ship with. It's very convenient, and like it will automatically generate all of the code that kind of converts between Python and C++ types back and forth. So that gives you a really easy way to writing those C++ programs. The only difficulty you might still be facing is how do you actually compile them, because that's not usually very easy in C++. But we do provide 2 ways to actually do this for you. So if you want to be distributing your extension, you can like use a setup tools based method, which is like, the canonical way to create Python packages. But if you really want to hack on something really quickly, there is also like a one-liner that lets you import such C++ code. So you basically give it a list of sources, like relative to the script, I think. And it will basically, first time you call it, it will compile it and give you the Python module for this. The next time it will just load the precompiled module again. And then you can simply use this function as if, so like, in here it took like 2 tensor arguments, returned a tensor. At the bottom in here, it's pretty small, but like, you can basically use it as a Python function that, like, again, takes 2 tensors, returns a Python tensor. Your program doesn't really even notice it called like into your C++ code. And just to quickly go over the interface, I don't really want to get into details again, but that's an example of how, so that was the stable part. This has been here for some time and it will be stable. Now we get to the kind of preview part. So that's how you would define a simple neural network in Python. And if you were to do this the same in C++, that's how it would look like. If you have a training loop in Python, that's how it looks like. If you were to do this in C++, it looks like this. So it's really like mostly just syntactic differences between the 2 languages. But ultimately, we do have an API. Like, if for some reason you really need to run in C++, we really think you should use Python if you can. But like, if you want to embed in some runtime environment that only has a C++ API, that's still sometimes better to just write the code straight in C++. And now we have an API that exactly matches pretty much one-to-one with our Python API, and you can do that. So most of our packages for neural networks, gradient-based optimization, data loading, serialization, Python integration, and Torch script, again, are there. They're part of the preview, so they might change. But if you want to try, you can see. I'm really running out of time, but generally, like, the final thing is we have a new distributed backend. It's a complete overhaul. It has like new abstractions. It has some performance benefits. And some of the nice things is that it actually lets you write fault-tolerant programs. So, for example, if some of your nodes fail, you can still recover, and you can also like implement elastic sizing on on-spot instances and on some cloud providers to kind of lower the costs of your training. Finally, we're also working on integrating with Cafe 2. It's not very much user visible, but ultimately Cafe 2 is like merging with PyTorch to become PyTorch 1.0. They have a lot of great mobile kernels, so the mobile story will be generally getting better. So I ran out of time. Generally, PyTorch is supported by a lot of institutions, both academic and corporate. We have a really vibrant community. You can go into the forums. People will help you. They'll answer your questions. And I hope you'll appear somewhere in there as well. So thanks a lot.